Thank you, Paul. Thank you, Mark. Greatly appreciate it.
David.
Well, good evening. We're actually at the time scheduled to start the second technical panel of this track on low carbon building enclosures. Welcome to everybody. My name is David Gard. I'm the Executive Director of the Michigan Energy Efficiency Contractors Association. We're really excited to be one of the hosts of this conference. And we're in for a treat for this session tonight because we've got two real pros who are going to talk to us about low carbon building enclosures. I'm going to introduce both of our speakers and then hand it off to them to do their presentations back to back. And then hopefully we'll have a few minutes at the end to take some questions on both presentations. And I should also note that I've just dropped into the chat window, if you can see it, a link that you can use when we're done with this session, scheduled to be finished at 7:55, to go back to the original track. Also should be the same link that you used when you first joined the conference at 6. So that's what we'll use to go back. But for now, let me get right into introducing both of our speakers, Sigi Koko and Lucas Johnson. Sigi is going to talk to us about natural wall systems. She's a principal with Down to Earth Design, a company that she started back in 1998. Sigi designs exclusively natural buildings and teaches people how to build them. She has a master's in architecture from UT Austin, and among many other things that she does besides her specific design work, she teaches hands-on workshops. She's published extensively, and she also has been featured everywhere from the New York Times to HGTV. So we're really excited for her to kick us off with her presentation, and after she's done, we'll hear immediately from Lucas Johnson, who is with the Western Regional Manager with a company called 475 High Performance Building Supply. He is a building scientist who has worked as a builder, utility program manager, an enclosure system consultant, and a clean tech venture capital consultant. He holds a degree in physico-chemical biology and a master's of environmental science and eco-entrepreneurship. Lucas is in his dream job right now because he gets to collaborate with architects, engineers, and builders to make their projects cost-effective, carbon negative, healthy, durable, and enjoyable. So settle in as we have both of our speakers run through some material to us for us tonight that's going to be very helpful in the topic of understanding how to make a zero net energy structure from the perspective of the enclosure. So Sigi, I will kick it off to you. Thank you. Just to check with our track 2 organizer, John, can you hear Sigi?
No, I cannot.
Okay, Sigi, we have your mute button is showing green, so it looks like you should be allowed to speak, but we're not hearing you for some reason.
Now?
There you go.
Yeah, we're starting to hear you now.
Okay, is
Perfect.
the audio loud enough?
Yep.
That's perfect.
Super, and you can see my screen or no?
Yes, we can.
Yep.
Okay, super, okay, sorry about that. And I'm realizing I can no longer see the clock. So thank you so much for inviting me. It's quite an honor to be here. So I just wanted to run through sort of the anatomy of a natural wall system, and I wanted to start with the definition of what I call natural building. Lots of people have different definitions. This is to me, what does it mean? And it's basically the notion that you're going to use materials that are as local as possible when you can, that are available in abundance, that you can harvest without harming the environment. That means, you know, no over harvesting trees, but trees are fair game if you're not over harvesting. And then building in a manner with those materials that makes sure that you're not compromising energy efficiency. So I'm going to start from the bottom and work our way up. And so for me, every project starts with what's called a rubble trench foundation. And it's basically a low concrete, low site disturbance, low cost, high performing footer. And the idea is that you dig the width of a trench. The width depends on the bearing capacity of your soil and the loads of your building. So the width is calculated by an engineer. And the depth is calculated by your frost depth. So you go down to frost and do as wide as you need to create a snowshoe to support your building. And then fill that, line it with a filter fabric so it doesn't silt in, and then just fill it with gravel, tamp it as you go. And it only uses concrete at the top. And if you want to be a purist, you cannot even use concrete there. You can use a stone stem wall. And then the idea is that you're reducing the total amount of concrete. So for most footers, it's a minimum of a 75% reduction in concrete use. And the reason that's important is that cement production produces 1.25 pounds of CO2 for every pound of cement produced. So it's a very carbon intensive material, and minimizing it is then therefore beneficial. It's high performing because the whole footer is a drain, and water is the single biggest cause of problems with the foundation. So it's also called a dry footer. It was Frank Lloyd Wright's favorite footer. And then I do a wide variety of vertical structures, but I always build the roof first so that I have protected cover to build underneath. This can mean studs, this can mean post and beam, this can mean timber framing, it can mean any way that you want to get vertical. I try to use, when I'm using wood, local wood, site harvested wood whenever feasible. Oh, and just to let you know, I put a link on each page for more information about that particular topic. So that's what the blue link is on each page. When you're using natural materials, you want to, well, this is true for any building, but with natural materials, it's particularly important to make sure you have what's called a good hat and boots. So a hat, picture a wide rimmed hat to protect you from rain. With passive solar design, it's also calculated to protect you from overheating from the sun in summertime. But the idea is get materials up off the ground that might be prone to decay so that they're not damp. No moisture equals no decay. And give yourself a good roof overhang to protect the walls from inordinate amounts of rain hitting them. These are the same rules we use for conventional wood construction. So this is not new, it's just really extra important when you're using natural materials. So this again is site harvested wood for this structure, as you can see. And then we're doing infill insulations. I primarily use straw bales. They're stacked like big fuzzy bricks. I occasionally will use hempcrete, but right now that's quite expensive. So straw bales are just literally those rectangular bales you get out of a field from a farmer. I use them because I live in Pennsylvania. I work in the East. They are ubiquitous, they are inexpensive, and it supports the local grain farming after they've harvested whatever grain they're selling. The wheat is a byproduct. So it's local material and very low energy to produce and super high insulation. So the wall system is between R36 and R48, depending how well you install it. Either way, I'll take the numbers. And then hempcrete is the hurd from a hemp stalk mixed with a lime binder. And And the idea there is to create, and it's an infill system in a stud wall. So you typically would do alternating studs, infill with the hempcrete. It cures in place. It's more expensive, and it's usually not local, at least to where I am. There's a few places in the US where that's a local material, but not where I am. That's why I tend to not use it as much. But as the laws change and hemp becomes easier to grow, or shall I say legal to grow, then that cost should come down and it should be more local in more places. And then you want to protect the walls, but you want to use breathable finishes. And so what that means is vapor permeability. So we've protected from liquid moisture with our hat and boots, and then we're protecting the inside and the outside with vapor permeable finishes. That means they allow humidity to travel through freely, but liquid water runs off. And that means that water does not get trapped inside the wall system. And so on the exterior, it can be siding, but I typically use a lime plaster, which is what you see going on here. Lime cures into stone. So you're basically plastering limestone onto the exterior of your building. It's pretty doggone durable. And then inside, using very thick clay plasters. And the extra benefit, so clay plasters typically, you dig the foundation and there's clay in the soil, and voila, you have your material for your plaster just from the footer dig. So that's pretty doggone local. You just need to stockpile it on site and then sift it, and usually add some sand, some straw, and put it on the walls. The benefit of a thick plaster in a super insulated building is that the plaster acts as mass, which moderates the temperature inside the building. That means as you have temperature fluctuations outside, you will not experience those temperature fluctuations inside. Clay uniquely also has the benefit of regulating humidity. Whenever you have higher than 50% humidity, it absorbs humidity out of the air, and when you have lower than 50%, it releases humidity. So it's never getting wet. It's like a lung. It just pulls in, releases, pulls in, releases. And then at the top, I like to do vegetated roofs or living roofs or green roofs. It's essentially, think of it as a ballasted roof system. This does not replace the insulation that you need in your roof. 60% of your heat loss in winter and 60% of your heat gain in summer is through your roof. So insulate, insulate, insulate. But it's basically that you're replacing a ballast on a roof with plants that can handle no groundwater tables. So typically those are succulents that store water in their leaves. And then just a couple myths that are out there about natural building. So one is that you're not going to be able to get a building permit, and that's just not the case. And the reason is that all building codes begin with a paragraph that states that if you demonstrate compliance with the intention of the building code, then they must allow you to build. Then you are in compliance with the building code. So you have to just prove that your material meets the intention behind the building code. So does it meet the energy performance requirements for insulation? Does it meet the safety requirements for fire rating, et cetera? And there are third-party tests that have been done for most natural building materials at this point, for most applications, I should say. And so you can demonstrate that very easily. Those tests are generally for free online. Another is that you can't build straw bale in a wet climate. I hear that all the time. I'd love to do straw bale, but I don't live in a desert, so I can't. And the bottom line here is and the link here, I have a much more extensive article on this. I could do the whole 15 minutes just on this. But if you can build with wood, you can build with straw. They're both biodegradable. So that's the way to just debunk that notion. If there's a way to design it and detail it appropriately for wood, then absolutely you can do the same for straw. Yeah, so when you have a monolithic wall system with very thick plasters on, one of which turns into stone, you don't really have access points into your wall. And so bugs and rodents are not at all an issue. And you can absolutely get financing and insurance. And the reason is because you've built something that's code compliant. And so demonstrating that you're compliant with all building codes, that you have a building permit, that's usually all it takes to get insurance and financing. I will say the link that I'm showing here is currently offline. I'm not totally sure why it's been offline for about 3 weeks, but I'm including it because when it goes back online, it's a great resource. It lists all of the insurance and finance companies that have already done mortgages and insurance for natural homes. And kind of the heart of natural building to me is that the construction techniques are extremely simple. They're easy to learn. You feel like a pro in a few hours, as opposed to, you know, framing, which you don't feel like a pro in a few hours, not even in a few days. But it's also very labor intensive. So you're trading off material cost for labor cost if you hire somebody to do everything. But what it does mean is that there's opportunity for hands-on participation. So I have just 2 quick examples. So this house, their priority building this little cottage was cost. In other words, low budget. So this was under $75 a square foot, and it was built entirely with workshops and the homeowner's sweat equity. The only thing that was hired out was electrical, plumbing, and the initial framing. Everything else was done by people who had 0 construction experience. But you can also do extremely high-end, extremely luscious, sexy, natural homes. So this home in particular was their highest priority was quality. And so it was a team of craftspeople that built this home, all with site harvested wood and materials. And it was built by a contractor and various craftsmen. So I think I did my 15 minutes. And that's all I will leave you with is that's kind of my motto.
Sigi, that was fantastic. And I know, like you said, you could probably talk about 100 different topics in 15 minutes alone. But you've done exactly what we needed in terms of just giving us a sense for what this construction method is all about. And for folks who do want to follow those links that she had in her slides, we will have slides available to you, and I encourage you to go do a lot more in-depth research. This is something I think really inspires us, and I would expect to see a lot more of it going forward. So Sigi, thank you. And we turn now to Lucas from 457 Building Performance Supply or High Performance Building Supply. And Lucas, take it away.
Lucas, can you try to unmute? There we go.
Yep, sorry, it was that same thing that happened earlier where it was muted by host, but I think I'm here. You can hear me, right?
Yes.
All right, and are you guys seeing the presentation full screen here?
Yep, looks good.
Fantastic. All right, well, thank you guys so much for having me. We'll start with a quick introduction because I'm certainly new to this crowd. Currently, I'm calling you from Tucson, where we live. We also live part-time in Seattle. My wife and I are both from California originally. My background is in science. I have a degree in physicochemical biology, as mentioned, and got really passionate about climate activism and then using green building as the vehicle for that. As you just heard about, I mean, I cannot say enough about how much I appreciate and I'm in love with the project that was just presented about. It's exactly the kind of building I want to see more of. But getting natural building to scale has been pretty challenging. So I kind of joined up with a company that was focused on trying to apply as much natural building approaches as possible within a more conventional framing methodology and whatnot. And why am I here, I guess? Well, I met Michael Clement at the JLC Live conference when having those things in person was still a thing, and had some wonderful conversations. And I'm a bit of a, I guess, campaigner personality. That's what a recent personality test told me. And I love to share messages that I'm passionate about. And happy father. I've got 2 young kids, so definitely care a lot about creating a better world moving forward. And personally, outdoor enthusiast and soccer fanatic. So I'm also the Western Regional Manager for a company called 475. Our goal is to use building science to find the best products in the world and import them into North America to help us leapfrog from where we are to better building. So that's that. And you know, regardless of the region, we hear so much about how like the blower door is king. And what I mean by that as an analogy is we always look at efficiency as the be all end all. And efficiency is a wonderful thing, but we need to think about what we're delivering efficiently. So efficiency is a wonderful element of a project, but it's certainly not the whole picture. So kind of my snarky response is embodied carbon is queen. So if you look at the little red circle there, the operational use of building, that's the phase in which efficiency matters and occurs. I'm borrowing this slide from my buddies at New Frameworks, some absolutely fantastic people who are doing, you know, carbon storing, straw bale, panelized insulation, and all kinds of just amazing things. And anyhow, it's really important to look at this full life cycle of the materials that we use, right? And again, efficiency is great, but we need to think about a bigger picture. So here's a silly example. I mean, this is technically 0 operational carbon, but clearly this is a massive amount of embodied carbon for the utility delivered and just a silly way to do it. So like, it's just taking a point of, let's really look at what we're designing and delivering and think about why we're doing it. And we also always talk about efficiency, operational carbon savings as this guaranteed thing, but we need to recognize that they're highly variable over time and space. What I mean by that is people's behavior is pretty unpredictable. You know, people might put like 8 old plasma TVs into a passive house and overheat it or some crazy thing. Working on thousands of projects all over North America, I've seen a lot of crazy stuff happen. Less comically, certainly, the climate is going a bit nuts. So we don't really know how buildings are going to behave moving forward because we're basing decisions on models about past climate, not future climate. And the carbon impact of the grid is actually incredibly variable. And we'll talk about that a bit here. So the idea is, does efficiency save carbon? And of course it does, right? But the amount of carbon saved changes radically depending on your local grid. And one of the primary points is if we're going to try to save carbon, we need to stop talking about it in proxy units like kilowatt hours and BTUs and start talking about it in pounds of CO2, because that's a unit that can be used for operational carbon. It can also be used for upfront carbon, end of life carbon, and the full carbon life cycle of a building. It creates a common unit that we can use to talk about these things, right? So if we look at the fuel source carbon intensity, these are some averages I took from the Energy Information Administration's database from like 2017 sources. You can see there's different pounds of CO2 per kilowatt hour for these different sources. And then every year, utilities put out these power mix reports that show, or every 3 years, actually, I believe it is, they put out power mix reports that show the mix of their power sources. So you can get a rough idea of how many pounds of CO2 per kilowatt hour exist. So like in Seattle, on Seattle City Light, where there's about 94% renewables, you got 0.12. So let's just say around 0.1 pounds of CO2 per kilowatt hour, right? In LA, where it's decent, you got about 0.6. Tucson, where I'm talking to you from right now, there's about 1.8 pounds, which explains to you why this conversation is being brought to you by the solar panels on my roof, not the grid here in Tucson, because it's an insane amount of carbon per kilowatt hour. All right, so then we can look at, let's say passive house is the golden standard of efficiency, right? If we look at these operational carbon savings from passive house by region, and I apologize, I'm having to jump through a very complex topic quickly, so definitely happy to address questions. I borrow these numbers from utility program utility program work I've done over the years in California and the Northwest, and looked at an average kilowatt hours per year for a 1,500 square foot house. What percent of that is HVAC? If we save 90% of that HVAC energy by doing passive house, how many kilowatt hours are saved? Multiply that times the local pounds of CO2 per kilowatt hour, and then we have a rough idea of how much annual carbon savings exists in pounds of CO2 per year for a passive house on average, right? In a given region. In Seattle, it's not much. It's just over 1,000 pounds. In Tucson, it's almost 20,000 pounds. So a passive house makes a massive difference in Tucson, but it really actually doesn't save that much energy. And it's because Seattle City Light has done a great job tightening up building codes and has 94% renewable grid. So it's a good problem, but it's something we have to recognize if carbon savings is our actual goal. So again, from other perspectives, this is from Architecture 2030. Why does embodied carbon matter, right? Well, if we look at the timelines that we have to deal with the climate crisis, we're looking at 2050, we're looking at about 80% materials and construction, so embodied carbon, to about 20% operational carbon impact is the total carbon impact by that date. If we're looking at 2030 as the revised date, which the IPCC just put out last year, then we're looking at about 90% on average. And in an area like Seattle, it's about 99.9% or something of the impact is the embodied carbon of the building, not the efficiency by the date of 2030. And the way we like to say it is maybe a weird analogy, but it works, is why gain weight to lose weight? You know, if you're gonna go on a diet, it makes no sense to eat Twinkies for 3 weeks, put on like 30 pounds and then try to lose it. We do this with buildings. We add tens of thousands, if not hundreds of thousands or millions of pounds of carbon up front in just the insulation materials alone, and then say, oh great, those insulation materials save a bunch of carbon over time, but when does that actually pay back? And it turns out that answer is really not that complex at the residential scale. We can look at these things. So like, we need to stop doing this. It's not a very efficient process. And the importance of embodied carbon is going to grow constantly over time, right? Buildings are becoming more and more efficient. The energy supply increasingly uses locally produced energy or lower carbon sources. We have massive grids that are decarbonizing. There's a lot of reasons, but basically embodied carbon is going to matter more and more, not less and less. A lot of my career has been focused around high efficiency building, net zero, passive house, living building challenge, et cetera, et cetera. And so airtightness and insulation has been a core element of my career, and building science is kind of the main profession that I guess the core of everything I've done in my professional life. And what I've found working on thousands of projects now, mostly at the residential scale, is that insulation is a really massive element of carbon impact if you think about the volume of insulation used. And it's also the thing that people care the least about. It's easy to get people to change it. And the best options for carbon are also the best options for the people. You know, we need to minimize concrete and steel and framing and try to use FSC wood, but that can be tough with engineers and budgets and all that. And then changing finishes, great, we should do it, but it's really a hard conversation with clients a lot of time. So insulation is just something we can change right away because it's really not hard. All right, so we can look at a few different areas of embodied carbon of insulation. Again, this chart that you're seeing on the slide here is from Architecture 2030. And we can see options like high density spray foam and medium density spray foam are just massive. This data for XPS is actually a bit inaccurate. XPS is closer to medium density spray foam. The XPS data in this was actually used from a European database where they use HFO instead of HFC blowing agents. So XPS could get this low, but it's not nearly this low yet. EPS, less bad. Mineral wool bats, less bad. Fiberglass bats, less bad. But then the cool thing is we actually have options that are carbon storing up front in their life cycle. So we can subtract from our upfront carbon budget, if you will, right? So there's wool, dense packed cellulose, cork, hempcrete, straw bale. Straw bale is amazing, made locally. That's one of the things I'm the biggest fan of. And then there's wood fiber, which is highly debated because there's actually a lot of really bad wood fiber products out there. But if we look at these things in a specific product way, we can look at, you know, environmental product declarations and figure out that certain wood fiber products do save a massive amount of carbon per cubic foot. And I think, by the way, it's very important to talk about this in pounds of CO2 per cubic foot, because a cubic foot's roughly the size of a basketball. So you can have someone imagine holding a basketball and thinking about how heavy it is. You know, the wood fiber, dense packed cellulose wool, these carbon storing options would be floating, right? And then closed cell spray foam would be like 100 pounds in a basketball. That's insane. And just that visualization, I think, really helps to explain this to our clients. So breaking it down into some basic rules here. First rule is maximizing sustainable wood framing and minimizing concrete and steel. But as I said, that can be difficult, right? So rule number 2 is to use healthy, natural, vapor open carbon storing insulation options. If we're going to do nothing else, let's at least do that. But then we need to surround that insulation with proper vapor permeable airtightness that promotes drying potential as well as airtightness. And that was amazing to see all that pointed out as well. Part of the reason I'm a huge fan of natural wall systems. So here's a little analysis that I was doing for a project in Seattle. This is basically looking at a passive house versus if you've heard of a pretty good house standard. We looked at a foam-based passive house, and this is just the embodied carbon of the insulation alone. And what we're looking at is how much embodied carbon the insulation adds versus how much embodied carbon the insulation subtracts through operational carbon savings by 2030. And you can see that a foam-based passive house is certainly not worth building from a carbon standpoint in Seattle. If you use carbon storing healthy insulation options, then you can have upfront carbon storage from your insulation that's added to by the operational carbon savings and get a good chunk of carbon net removed by 2030. Less bad passive house, which is, you know, fiberglass and mineral wool. In Seattle, that doesn't actually save net carbon, or it's very, very unlikely to save net carbon, because this is the insulation alone. This is including site work, concrete, you know, framing, all the other stuff, flying in custom kitchen stuff from Italy, whatever. It doesn't include any of that kind of carbon impact. This is just the insulation alone. So we need to make sure our insulation at minimum is creating net carbon savings. All right, so let's look at a project I did in Seattle. This guy bought a house. He's named Sidney Beaumont. He's a climate film documentarian. He did Paris to Pittsburgh and a few other amazing documentaries, and bought an old house in Seattle and wanted to retrofit it. And he was looking at using mineral wool because that's what the builder he worked with was used to using. And he and I got to talking. So we were looking at carbon impact because that was his main goal of doing this retrofit, right? Keep the whole house in place and add something that minimizes the carbon impact to it. So we looked at a less bad retrofit. We don't need to go over all these specific numbers because we don't have time. But the point is there was like a significant carbon payback, about, you know, a decade or so. But then we looked at this, you know, quote unquote good wood retrofit scenario, and we were able to build in about 12 years of operational carbon saving equivalent up front. So that change from mineral wool to wood fiber exterior insulation alone on the, and also going from, fiberglass to dense packed cellulose on the inside, resulted in the equivalent of about 21 years of operational carbon savings. So now this is a house that is almost surely carbon storing up front because it's a house that almost nothing else changed. It was basically a shell retrofit. Now let's say I was done with my arch nemesis spray foam insulation, which, to be fair, I installed hundreds of thousands of square feet of before. As a scientist, I had to collect data about it and reject my hypothesis that it was even a remotely good solution. My apologies if anyone is a fan of spray foam, but I don't like it. And this is one of the reasons why. If you look at the carbon payback, it's just ludicrous. So another reason is if we think about, you know, social justice and all that, which is obviously something we really should be deeply thinking about. Look at how that guy is dressed up to install that. It's not a safe, healthy material. And I think it's incredibly unfair that we ask people to expose themselves to these products. So yeah, I'd ban foam if I was king for a day or whatever. So this is the house, just to show you. Here's the carbon storing wood fiber insulation going on. This was storing something like 20 pounds per carbon per board here or something like that. Gets covered with your proper air tightness, vapor control, and you know, water control. So this is it's like putting a hard shell over your ski jacket when you go skiing. buildings properly wrapped. You can see ventilation battens starting. This is a Victorian, so it's extremely, well, not quite Victorian, but sort of that style. Very, very complex shell to do this around, but you know, cutting wood, you can do it with standard carpentry tools, so it's easy to do, relatively. On the inside, there's some reclaimed fiberglass bats. That a couple unopened bags were found in the attic, so we use those. And then there's dense packed cellulose in the walls, and there's an interior air barrier and smart vapor control membrane installed. The window detailing, normally I stuff sheep wool around the window and the shim space, but they were actually able to rip extra boards of the wood fiber and stuff the wood fiber around the windows. I lost a $20 bet on this because I didn't think they could do it. But in the end, it looked like this, and you know, met passive house air tightness standards and used carbon storing insulation for a retrofit, ENERFIT standards, so below 1.0, not 0.6. I think it was like 0.8. Oops. And I went a little early there. And you know, it was an awesome project, super fun to be part of, and very meaningful. And there's a lot of movement towards this. One of my favorite organizations I'd recommend if you want more information is Builders for Climate Action. It's an amazing coalition of experts. They have a wonderful website. They have a white paper you can download for free. They have a carbon calculator targeted at the residential scale, which is a first, coming for like kind of whole building analysis, whereas the analysis I focus on is usually the control layers, the performance measures, the carbon impact up front of that. But they're including framing, foundations, finishes, all that stuff. This is a little graphic they have about basically how we can use carbon drawdown of natural resources. And then obviously we have to put those resources through a high-tech process to create what I call high-tech nature, right? It's kind of a weird thing because I'm not a big technology fan, but people tend to feel safer about it if you call it high-tech nature. And then we have net carbon storage up front for the buildings that we have. And as they say, natural systems plus intentional human engagement equals net carbon storage. And I think that's beautiful. The EC3 tool is a much bigger kind of thing. It's a massive open source embodied carbon database for specific products. You see Stacy Smedley here in the background. She's from Skanksla Construction. She won an internal grant to organize Microsoft and some other organizations in Seattle like Sea Change Labs, the University of Washington, Department of Architecture, just amazing groups, right? Yeah, there's this whole thing called the Embodied Carbon Network you can join now for free if you want to be part of this conversation. And a group I'm deeply involved with, the Northwest Eco Building Guild, through our Shift Zero branch, we helped out there. You can see in the upper right here, this is a little screenshot of what the tool will do, looking at different concrete options, where you source it, how you put it together, et cetera, to see like, okay, well, you specifies this, but are there savings? So my challenge with this tool is it's very much targeted at large buildings and kind of incremental approaches like less bad concrete. And for large buildings, I'm actually fine with that overall, because they're a pretty low percentage of the overall carbon impact of the built environment. But for single family and small multifamily, where we can very much do, hopefully all the way to true natural building, but if nothing else, use healthy natural insulation and performance measures, you know, why wouldn't we really? And it just makes such a huge difference in the residential scale. Whereas for, you know, concrete and steel for large commercial is a much bigger portion of the overall impact. All that being said, one last thing worth noting is that a buddy of mine told me that he ran an analysis on a large commercial building for downtown Vancouver, BC, and XPS insulation was equivalent to the entire carbon impact of the rest of the building combined. So the XPS insulation was equivalent to the concrete and steel for roughly, I think it was a 20-story building. That blew my mind. All right, enough said there. I'm working on a project called the 5 Factors of Good Building. It's a couple decades of experience being put together to kind of create a quantitative way to look at holistic good building. It can be high performance, low performance. That's not really the point. That's part of it, but it's not really the whole thing. So we look at comfort and health, efficiency and renewables, durability and resiliency, social equity, and what I'm calling embodied injustice, like having to install spray foam, and then life cycle carbon impact, like what we're talking about. And the idea for this is to be open source, housed in a nonprofit. It's in a beta version now. We're trying it on a few projects. Seems to be pretty influential with decision making and working well. But there's a lot of work to be done, and your help would be awesome. Any comments, feedback, all that's much appreciated. I'm going to skip through this because I'm short on time here, but I do want to show you one thing. I'm a real building science nerd, so I love stuff like thermal diffusivity. But effectively, here's the backyard experiment I did, which is a more fun way to put it. The box on the left is 1.5 inches thick, made out of wood fiber insulation. The box on the right is 2 inches thick, made out of XPS. And, you know, there's obviously a huge amount of carbon storage per cubic foot or whatever in the wood fiber, and a huge amount of carbon impact in the XPS. But the thing that people often say is, well, the XPS has higher R value, so it's worth it. And all right, well, let's see. So I put hydrothermal sensors in the side of these boxes and put them in my backyard in Tucson for about a year. This is years ago now, so this is our old backyard. And made sure the boxes weren't shading each other, tried to create them as exactly equal as I could in size, dimensions, sun exposure. Left them outside for a whole year. This is a week of the most interesting data. It was in October, around this time of year, where we're getting temperature swings from like 30 degrees at night sometimes to 90 during the day. So we're going to see, you know, a little more value of thermal mass, of course, in that kind of temperature swing. But I was shocked the difference. And anyway, the idea is inside the wood fiber box, you know, it was 52 to 90 degrees. Inside this R10, you know, basically double the R value, it was 48 to 115. So there's a huge discrepancy between rated R value and real world thermal performance. And we also need to look at humidity distribution, which is basically safe inside the wood fiber box and is terrifyingly bad inside the foam box. You can see it kind of sneaking in there at the bottom, 13% to 94% if you can't read that. Yeah, we like to say we need to build like the future depends on it, right? We have a thing called the Smart Enclosure System. There's a ton of free ebooks and resources you can download to learn all kinds of things about this. It's not really stuck on a single building methodology. It's based on these principles that you can read more about later. And kind of the core idea is it's unwise to pay, you know, too much, but it's worse to pay too little. We need to find the right value, and we need to think about what outcomes we're really going for and talk about it in the right units, right? So if we're going to save carbon, we need to talk about it in the units of carbon. So a question I always ask is, you know, this is to take, you know, beyond this is, what next step can you take based on what you learned today? And I really appreciate any help in spreading the word. You know, hard to control the impact of framing and finishes, right? But we can definitely change insulation. So let's at least make that happen. And then any other ideas you have, I'd love to hear them. And that's what I got. This is my older kid already getting engaged in backyard building science with me. So that's fun. You may hear my younger kid just shouting in the background there. So yeah, I'm gonna wrap it up there. And thank you so much for letting me join. I'm sorry I didn't have any project examples in your region, but you know, we all need to work together across all these regions to make this happen. So wonderful to join. Thank you.
Well, Lucas, thank you very much. And I know it's just about time for us to go back to the plenary. For those who want to jump, go ahead and do that. But I do have one question. First of all, thanking both Sigi and Lucas for their time today, and just a quick introduction to some of these really great ideas. But Sigi, if you can turn your mute button off, because one of the questions that came in is actually for you in terms of talk about the lifespan of natural building materials. You know, does it vary a lot by material, or what are you kind of seeing in terms of design life, and how do you need to think about that when you're working with natural building systems?
Oh, it's a great question. So the oldest buildings in the world are natural buildings. The oldest buildings that exist today anywhere in the world are by definition natural buildings, because they were built with local materials from nature, found in abundance, and built climatically because they didn't have mechanical systems to override nature. So they had to build them for their climate in a way that was livable. So durability of natural materials is exquisite, and I would say outperforms standard construction. I think the question probably has to do with straw bale and the notion that, oh, it's gonna rot. Nothing rots if it's not wet. So it requires 18% moisture content in order for decay to begin. So dry wall equals wall forever, and there are straw bale buildings from the 1880s that still exist today. They're the first straw bale buildings that were ever built.
I can't think of a more perfect note to end our session on. Unfortunately, we do have to go, but I want to thank Sigi and Lucas. I encourage everybody, when you get the slides from the conference, go back and really study the slides that we didn't have enough time to really go through in detail. Go to their websites. You'll have that information as well. They're doing fantastic work. Thanks everyone for joining us tonight. Thank you all of our sponsors, and you can jump back to track 1 to catch the very end of the first day of the conference. There's a link to that in the chat box that I put in early in this session, and it should also be the link that you originally joined tonight when you went to the plenary to begin with. So thanks again, everybody. We appreciate you joining us tonight.
Thank you so much.
Thank you.